everyone. This is machine learning software 28. We're going to basically look at our project that is on deep acoustic representation learning for class respiratory disease detection in resource constrained environments. So we are simply looking at raw resource environments and also uh, multi-class way of detecting respiratory diseases. Yeah, so below here I just have my group mates, that is of Roth Jim Frank, Warusimbi Ashraf, one speaking this opinion. So we are all from Makerere University, and our supervisor is Dr. Garwango Marvin. Yeah, so below here I get the contents of our presentation. Here I have the background introduction. Yeah, so on this slide, you can see that on the right, I'm having a map of Africa showing the sub-Saharan Africa, how the TB burden has been prevalent in this region, as reported by World Health Organization in 2022. So the dark shades show high burden areas, and this has been due to the raw resources in these regions, the limited specialists, and then diagnostic tools, just as the auscultation stethoscope that can be used to maybe work on these respiratory diseases. So our project that has been given a short name, RespiroSense, aims to solve this by basically using cough sound as a biomarker that can be used to pre-screen respiratory disease cases and trigger right responses without maybe using a lot of resources. Yeah, so I would simply term this as turning cough into a diagnostic signal. Yeah. So on this slide, I have the related works, but basing on our literature review, uh, all these simply focus on binary way of classifying. So it simply classifies normal and abnormal, and they also do focus on cycle level breathing sounds. But yeah, so these don't have any existence of lightweight, maybe multi-class systems. Yeah. So as the rest process, we are looking at addressing addressing that matter with uh, coming in with a solution that can work on that can classify in a multi-class way, and also work in noisy environments, and then low resource deployments. Yeah, so the problem statement simply shows that we have the TB and these other respiratory diseases people fail to detect them early because of one, limited specialists. Then we have few pulmonologists available. Then we also have we have uh, we have limited tools. We have no X-rays in such a low resource regions. We have no PCR machines in basically the rural clinics, and we also have limited infrastructure for maybe the solutions present. You find that in these rural clinics, the internet is not stable. We have unreliable power in such regions. Yeah. So our research questions want to develop a sound-based system for pre-screening respiratory disease. We want to build a lightweight deep learning model, the model suitable for all resource settings. We shall also evaluate the model's performance and assess the feasibility uh, in these regions. So research questions, research contributions and outputs. Of course, we developed the RespiroSense and we built a lightweight deep learning model, trained and evaluated several models across different demographics, also devices. So we designed a reproducible framework for co-sound respiratory disease classification. Yeah, so next is our methodology. So this from this diagram here, you see that we are starting with is data acquisition. So this data is, of course, got it from we got it from the public data sets and also cargo. So having gotten that data, of course, we collected it and standardized it into a WAV format. So from there, the data processing, of course, takes place within this part, and we are able to acquire 36 acoustic features. So these are MF pieces, and we have spectrocentroids, we have ZPRs, and RMSs. So from here, we then carried out feature engineering. With feature engineering, this what I mean, we tried to put out noise, and from here, of course, our methodology heads on to the modeling. Well, with my group members, we were able to have 12 model architectures. Yeah, so then from there, we were able to select our best model and then deploy it. We converted it to a TF Lite, deployed it to Android, and of course for real-time inference with drift monitoring. So the dataset description, and in our dataset description, we of course had 2,000 recordings, and this is of course balanced across all the 4 classes, where we had 500 for each. Then our key PDA visualization of gender distribution that has been illustrated here. You see that we have balanced gender distribution across all the classes, and we have future correlation matrix. Then we also have the TCNA projection. Yeah, this confirms that class separability in future space. So you can see that from this projection, you are able to see that our classes are separable, and of course the clusters are distinct. So this means that the acoustic signal contains disease-specific information. As you can see on this key here, we have in red showing TB, so meaning the features of TB are separable from the rest. So the blue is showing COPD, but the only issue was with COVID-19 and the normal cough. Yeah, so this it shows that it will be hard to a little bit classify COPD, COVID-19 and normal cough. Yeah. Then on our architecture, we had over 12 architectures where 4 came from each person, and here I'm going to talk about each of them. So I'm having the MLOP. So in our MLOP, you find that we do the future inputs at this level. After doing the future inputs, after doing the feature input, of course, we go to the dense block where we have batch normalization. Batch normalization basically stabilizes the activations. Then we do a dropout, a dropout of 0.3. So we're using a dropout of 0.3 to improve our generalizations. Then for the dropout, we go to the block 2 here. At block 2, we are simply you see that the model simply runs high level classifications, and but still also batch normalization is applied, and also a dropout is also applied at this level. So the process that takes place here is similar to that which occurs in the first block, but you find that at this level we are trying to reduce the number of filters from 256 to 128, and then from there it heads here, where still it goes into a dense block where here we are using 64 filters, and from there we go to the output. At the output part, of course, we are outputting the 4 classes, and of COPD, COVID-19, the health bit. Yeah, so with the one DCNN, so it also starts with the input layer, and we then head into the first convolution block, and then from there it goes into the second convolution block, and from there it heads into the global aggregation. From the global aggregation, it will of course head into the dense classification, and of course output the our output is based on any of the four classes. From there, I will go, of course, to the transformer model. Transformer model also does input, then projection, and then it has what we call a feed-forward network, pulling and then output. Then I'm having the one DCNN with attention. Simply, the process is still the same, input, and then this one has what we call masking. It does the masking and then convolutional feature extraction. So due to the limited number of slides they've given us, we could not include the mathematical grounding of all these models, as this was consuming a lot of space. So I'll head into the deep neural network. So the deep neural network, which is just below here, the deep neural network, of course, it does what we call feature extraction. At this part, we are able to extract 36 acoustic features. Then we from there, these 36 acoustic features that are taken into the forward pass, where it goes into this layer. At this layer, we take it through the batch normalization. After the batch normalization, we then head into the softmax at this part. At the softmax, we are trying to output. Our output will be, of course, based on the what? The four classes. Either COPD, TB, COVID-19, or health. Yeah, so this show just showing output of results from these are confusion matrices showing output of results for each of the models. Yeah, so I can just maybe look into one of them here. Just this shows that the model is performing well for COPD and TB. It is simply struggling with COVID-19 and then the health a bit. Yeah. So I'll then go to the quantization and the model compression, where we tried to employ two techniques. That is quantization and then knowledge distillation. So in quantization, we are going to simply train, or of course our trained models are normal of float 32 weights. So for what quantization does, it takes the model through a post training, where it is going to convert the the these float 32s into int 8, and yeah. So we are basically trying to reduce the model size, so it into these lower sizes. So what quantization does is, of course, it converts weights to lower precision, maybe float 16 or int 8, and then the result is a smaller size model. So on looking at knowledge distillation, with knowledge distillation here, we see that we have what we call a teacher model and a student model. Our large model, of course, trains a student. So this student learns in two ways. It may learn from the hard labels or the soft labels. With the hard labels, I mean this data, maybe the true classes, like us doing normal training. But with soft labels, the student learns from the teacher's outputs. Yeah, so with that, we have, of course, smaller model that mimics the teacher's behavior. Yeah, so with me here, of course, I'm having the table summarized results that we had before us carrying out the compression. So you see that this side accuracy accuracies may not improve greatly, or some may reduce slightly, but what we have achieved so far here you like now for the MLP, you can see that it reduced greatly from 5.8 MBs to 3.2. Now, when you come to this, now look at the ResNet 50. It reduced from 96 MBs to 356 KB. So you find that this really contributes a lot on our aim to of course deploy these models in resource constrained environments like the mobile phones. So what I have here is of course our deployment pipeline. Having chosen our MLP as our best model, of course when you deploy it on a mobile phone, you find that a user will come, maybe have their record their cough sound. We try to of course extract the features. Once these features are extracted, of course, they're always 36 in number. Then of course there will be the safety in what the safety engine does. It will do, of course, put it into the class probabilities, and after that, it will apply, of course, the confidence thresholds, and then you see that what we get back is diagnosis. You get the diagnosis of this person, and then maybe the referrals. What are the recommendations for that? Yeah. So what I'm trying to show here is basically our deployment platform. So we deploy the RespiroSense on a phone, where of course we have a simple mobile app. So this is basically the link to the APK showing just so RespiroSense here. Someone is coding, and here they have output features. Yeah, so these are basically limitations we had, the data set variations in coding. Yeah, so and of course, these are all references and acknowledgements. Basically, I want to appreciate Makerere University and College of Computing and Information Sciences, our lecturers, and then Allison.com, where we first started the journey by learning the basics that, of course, have contributed to this project. Thank you.